So I'm going to do, in this case, actually, you could isolate either of those two members, but I'm going to isolate the 50 kilogram cart. So the forces, you have the weight acting down, that's 490.5. You have the normal force, I'll call that N50, acting up. And then you have this force F. And this represents the force vector that we're trying to calculate. Any questions about how I set that up? So Newton's second law says F0 plus 0 N50 plus 0 negative 490.5 is equal to the mass, 50, times the acceleration vector, and now we know what that vector is, so 2.270. And this vector is the force vector acting on the 50 by the 60. The first equation says F is equal to 50 times 2.27. So F is equal to 113.5. And then plug this variable value back into the vector, and you get F on 50 by 60 is equal to positive 113.50. And so the force vector on the 60 by the 50 is negative 113.50. Any, yep. Uh-huh. Right. I would prefer that you don't do it that way, yeah. Because I think like sort of seeing how the basic laws fit together is a good thing to do, you know. And the problem with any kind of shortcut, I mean, you're right, and that, you know, you figure that out pretty quickly. The problem with any kind of shortcut like that is there are always like exceptions, things that you can't use it on, you know. So
So when we're doing this three body diagram, in cases like this where we've got the cards that are attached together, if we isolate the ones that always going to be this first one that we're looking at, so if we had drawn the 60, we would have gotten the answer for obviously the force on the 60.
right,
Okay.
that's right. Remember, sometimes like if you have multiple, say you have 5 carts in a row or something, you can't isolate any of the interior ones. You have to work in from the outside, um, but yeah, what you're always calculating is are the forces on your isolated body. Yeah, let's do that because I think it's a good exercise to see how you get the same thing. Okay, so I'll do that. So if you draw a free body diagram of the 60 kilogram cart, then you have the weight that's 58, no, 588.6. You have a normal force N60 acting upward. You have the tension over here that we know is 250. And you have the force here that, let's call that R. Okay. And so Newton's second law says 250, 0, plus 0, negative 588.6, plus 0, N60. And now what are the components of this force? Yep, it's pointing in the negative x direction, so this is going to be negative R0. That's equal to 60 times the acceleration vector, 2.270. And what we're trying to find is this vector. This vector here is the force on the 60 by the 50. And so the first equation says 250 minus R is equal to, can someone calculate 60 times 2.27? 136 point what? And so solve for R and you get 113.8, I think, in this case, right? That's just round off error, the difference between the 113.5 that we had before. Okay, so R is equal to 113.8. Now plug that variable value into the vector and you get that the force vector on 60 by 50 is equal to negative 113.80. And so Newton's third law says the force on the 50 by the 60 is positive 113.80. So this agrees with the other approach. Within our, round off error. Yep.
So if you're only considering the x value, why would you even consider y value?
Yeah. I guess just because I like to set it up in a general way, and if I had asked you for any of those normal forces, then you would have needed those y components in there. But yeah, I think it's good to think about them as vectors. You're right, there's some, like you guys found a couple of cases of shortcuts that could let you solve these a little bit quicker. But again, that falls into the category of shortcuts that would work in some cases, but would, you wouldn't be able to use all the time. All right. So now I want to do one more example that is related to this week's lab. So let's say that we have a mass of 1,000 kilograms connected by a cable to a cart that's, let's say, 500 kilograms. What's the acceleration of the cart? So I think when you first look at this, for a lot of people, the first reaction is, okay, well, that cable, like this is pretty similar to the other one, except that now that cable tension, instead of being, the cable tension before was 250 newtons, now it's going to be 1,000 times 9.81, okay? And that force is going to be accelerating this to the right. Well, actually, the cable tension is not going to be 1,000 times 9.81, okay? And the reason for that is that these are accelerating, and we'll see how that works. The way you have to do a problem like this is you have to do free body diagrams and Newton's second law for both of the two, okay? And then recognize that the acceleration down of the 1,000 kilogram mass is equal to the acceleration to the right of the 500 kilogram cart. That has to be true as long as this cable isn't stretching. And by the way, for smart cocktail party banter, that's called a kinematic constraint. You know the kind of cocktail party I'm talking about, where you're talking about physics problems. Feel bad for me. I actually have to go to those kind of cocktail parties. So let's first isolate the hanging mass. There's a weight force acting down, 9810 newtons. And then there's a tension force acting up, T. And so Newton's second law says 0T plus 0 negative 9810 is equal to the mass times the acceleration. And what do we know about the acceleration here? It's only moving in the y direction. And okay, so let's just say that. Let's say it is going to be in the negative y direction. So you could make either of those two assumptions and you could figure this out. But let's say we know that it's going to be accelerating down. So I'm going to call this 0 negative a. Okay. So we have one useless equation, and the second equation says T minus 9810 is equal to negative 1,000 a. So, whoops. Okay. So from the other one, we have T minus 9810 is equal to negative 1,000 a. And now I'm going to do the free body diagram of the cart. So there's the weight acting down. That's 4905. There's a normal force acting up. And the only other place that there's contact is the cable. So that's a force. And, you know, since it's all one cable going over that pulley, that has to be the same value T. And now Newton's second law says 0, negative 4905 plus 0 n cart plus T 0 is equal to the mass, 500, times the acceleration vector. And now this is where you have to use that geometric constraint. We're assuming that the hanging mass has a downward acceleration of a, right? So according to our kinematic constraint, we're going to assume that the cart has a rightward acceleration of a, an acceleration of a in the positive x direction. Okay, so now I'm going to write this as a0. Okay, where that a is the same variable. Whatever a is, if it has a downward acceleration of 5 meters per second squared, then the cart is going to have an acceleration to the right of 5 meters per second squared, and that's what we have with that constraint now. Okay. The second equation, that would give us the normal force, but we don't care about that. But the first equation says T is equal to 500A. And now we have a system of two equations for two variables. We can take this equation, substitute it into this one, and you get that. So T is equal to 500A, so I'm going to put 500A in place of T in that first equation. So 500A minus 9810 is equal to negative 1000A. Add 1000A to both sides, you get 1500A. Add 9810 to both sides, and you get is equal to 9810. And so A is, can someone divide that? 9810 divided by 1500? 6.54 meters per second squared. And so now the acceleration vector of the cart is this with the value substituted in, and you get 6.54 meters per second squared, 0. Okay. And then if you wanted the acceleration of the hanging mass, you'd substitute the 6.54 into this acceleration vector from the other Newton's second law. Any questions about that? So far, all of the problems that we've done have had horizontal surfaces that the things are sliding and rolling along. So I want to show you an approach that simplifies the math in cases where the thing isn't moving along a horizontal surface. So you can think of this as just a trick. I mean, you wouldn't have to do this, but the math would get pretty messy. So this is a trick for problems involving sliding or rolling along non-horizontal surfaces. And the trick is, now remember, we haven't fiddled with the coordinate systems at all. Like we've always just used a standard coordinate system with the positive x-axis pointing to the right and the positive y-axis pointing up. But when I first started talking about vectors, I was talking about how we can always choose the coordinate system as long as you follow the rules. Remember, x and y have to be perpendicular, and you can have a rotated version of the standard coordinate system, but not a flipped version. So now what we're going to do on problems like this is we're always going to align the x-axis with the surface, parallel to the surface, so that the positive y-axis points out of the surface. So for example, if you have a problem like this, where an object's rolling along an incline, say that this angle is 15 degrees, you're going to choose your coordinate system with the y-axis pointing perpendicular out of the surface and your x-axis parallel to it. As long as your y-axis points out of the surface, there's only one place your x-axis can go because of the no flipping rule for the coordinate system. And so a free body diagram in this case looks like, and actually let me do, so let's say that we also have a force pulling it to the right up the incline of 250 newtons, okay? So a free body diagram, there's the outline. There's the weight acting this way. So that's mg. I didn't give the mass. There's a normal force, and remember, the normal force is a pushing contact along a flat surface. And so the direction has to be perpendicular to the incline, toward the chosen body, away from the contacting body. And that 250 Newton force is this way. So what's the benefit of making this, using this sort of unusual coordinate system? You're basically, you're getting a lot more vectors that have one non-zero component and the other component zero, okay? And it makes the math easier to do. So like in this case, so here's the benefit for this example. The 250 Newton force is now just the vector 250, 0. Okay. The normal force is the vector 0, n, because it's in the direction of the y-axis. And notice that both of these, if we were using the standard coordinate systems, they'd have all these cosines and sines floating around. Okay. And the last benefit, it doesn't show up in the free body diagram, but the acceleration is parallel to the surface. So the acceleration vector is a0. Okay. So that's 3 benefits. The drawback, the trade-off is that in a horizontal vertical coordinate system, the weight is always really easy to deal with, right? Because it just acts in the negative y direction. Now the weight of this thing is a mess. The weight is, let's see, mg times cosine of 255. And I'll talk about how to figure these out later, but mg times sine of 255. Okay. So the good news is all these things. The bad news is the weight is ugly now. But you can see the benefits, outweigh the drawback.
You need a coordinate system in that's the neural forces, so you know which way it's going.
Here in the free body diagram. I would rather if you put the coordinate system in like a drawing of the picture, but not in the free body diagram. We're going to see that there's actually one other benefit will come up when we start talking about friction, and that's that the friction force is always parallel to the surface. And so that's another force that comes in that's easy for us to deal with in the rotated coordinate system. And, the trade-off is we need to come up with this new way of dealing with the weight. That's all. Okay, so yeah, let's do an example problem. So let's say that this angle is 45 degrees. And we have a cart that's 50 kilograms. And a force of 100 newtons pushing it up the ramp. And we want to know the cart's acceleration vector. Well, this surface isn't horizontal, so we know we want a rotated coordinate system where the y-axis is pointing out of the surface. That means that the x-axis has to point this way. A free body diagram has the weight force acting down. That's 490.5 newtons. The external force of 100 there. And then a normal force pushing perpendicular to the surface towards the body. Okay, so Newton's second law. What are the components of this 100 Newton force? Negative 100, 0, yep. And what are the components of the normal force? 0n, and actually that one you can just always bank on the fact that that's going to be 0n. That's because of the way that we're always going to set this up with a y-axis pointing out of the surface. So 0n. And then the last thing we have to deal with is the weight. In order to figure that out, remember that to come up with the angle, the counterclockwise angle from the positive x-axis, put the vector at the origin of the coordinate system. So there's the x-axis, there's the y-axis. Here's the negative x-axis, here's the negative y-axis. And does anyone have a feel for what this angle is? This is the key angle that we want. Well, it's 45, and I think the way to think about it is start with the standard coordinate system and then rotate it into the new position, and you can imagine what this 270 line is. That 270 line moves with it as you rotate it. And so if you move the coordinate system 45 degrees this way to correspond to this, you're moving that 270 dotted line 45 degrees back this way. Can you visualize what I'm talking about? So this angle is 45 degrees. And that says that the total angle going from the positive x-axis to this weight vector is 90, 180, 270, plus another 45. And so what's that, 315? So 490.5 times the cosine of 315 degrees, 490.5 times the sine of 315 degrees, and that's equal to the mass times the acceleration. This is another thing that you can always the acceleration is always going to be a0 if you choose the coordinate system the way I described it. Okay, so the first equation says negative 100. Can someone calculate 490.5 times the cosine of 315? Okay, so positive 346.84 is equal to 50A. And so we get 246.84 is equal to 50A. So A is equal to 4.936.8. Oh, I blacked out for a second. Okay, so that's the value of the variable. This is the acceleration vector. And so now just plug that variable value back into the vector, and you get an acceleration vector of 4.9368. Okay? So since we have a little time left, let me just go through a few examples where the hardest thing about this is just figuring out the angle for the weight force. So let's just do a few angles. you can get some practice trying to figure out what angles correspond to the positions. Okay, so first, let's say we have an object sliding along, you know, a wall. Let's say this is 10 kilograms. What's the weight, force, vector in the rotated coordinate system?